Good morning. Today we discuss about the chemical kinetics part 2. This is presented by G. Satyanan Gaud, Assistant Professor, Department of Chemistry, Dr. BRR Government College, Cherla. In this lesson, we discuss about the factors influencing rate of reaction. Which factors will influence the rate of reaction? That we discuss. The following factors will influence the rate of reaction: concentration of reactants, temperature, pressure, medium of reaction, radiation, and catalysts. They are the factors that influence the rate of reaction. Let me discuss about the concentration of reactants. All of you know that the concentration of reactants are expressed in terms of molarity, normality, molarity, etc. So the concentration of reactants, how the concentration of reactants will influence the rate of reaction. The rate of reaction increases with increase in concentration of reactant generally. The rate of reaction increases with increase in concentration of reactants. Why it is? At higher concentration, the number of reactant molecules per unit volume will be more. So that what happened, the number of collisions occurring between these molecules will be also more. All of you know that in order to occur a chemical reaction, the reactant molecules must collide with each other. When the reactant molecules collide with each other, they will convert into what? Products. I mean, the molecule which are possessing activation energy, they only convert into products. But in order to form the products, collision must occur between the reactant molecules. So at higher concentration, the number of collisions that occur between the reactant molecules will be very high, so that the rate of reaction will be more. That is the reason why the rate of reaction is more at higher concentration. We can also explain this with the help of the rate law. In Chemical Kinetics 1, we have discussed what is rate law. It is derived based on law of mass action as well as experimental evidences. For example, A and B are the reactants in a reaction. Now, for that reaction, the rate law is given like this. Rate is directly proportional to molar concentration of A power 2 into molar concentration of B. Right. So, what is the power of A? A power 2 and B power 1, we know that. Next. Doubling the concentration of A. Suppose if you are doubling the concentration of A, if concentration of A is doubled, what is the power of A? 2. That way it will become 2 square. Rate of reaction will increase by 4 times. Is it? But in this case, we have to keep the concentration of B as constant. By keeping the B concentration constant, if you increase the concentration of A by 2 times, then the rate will increase by 4 times because the power of A concentration term is 2. Increase in concentration of A is increasing what? The rate of reaction. Second point. Now you see about the B. What is the effect of concentration of B on rate of reaction? The concentration term B is having the power only 1, power of 1. If you double the concentration of B, rate also becomes double. If you triple the concentration of B, rate also becomes triple because 2 power 1, 3 power 1. If you increase the concentration of B by n times, rate of reaction also increases by n times. Like this, we can express the rate law as well as the effect of concentration on rate equation. So, at higher concentration, what happens? The rate of reaction increases. It is due to increase in number of collisions that occur between the reactant molecules. That is the reason. Okay. Next, let me see the effect of pressure. Let's consider the same reaction, but here we say A and B are the gaseous substances. This A and B are reacting in a container of V volume. They are reacting in what? V volume container. So what is the relation between the pressure and volume at constant temperature? It is given by Boyle's law. We know that when the pressure decreases, volume increase, or vice versa. Means we can increase the pressure or we can decrease the pressure by reducing the volume or increasing the volume. Like that we can change the pressure of the reaction mixture at constant temperature. Let's say again we are considering the same rate law of particular reaction. Rate is directly proportional to molar concentration of A power 2 into molar concentration of B. Or we can write rate is equal to K into, K is the rate constant or specific rate. So R is equal to K into, now we are expressing this molar concentration in terms of number of moles per liter, because that is the definition of molarity. Number of moles of substance solute dissolved in 1 liter solution. So R is equal to K into Na divided by V power 2 into Nb, number of moles of B divided by V. Na and Nb are the number of moles of A and B respectively. V is the volume of reaction mixture. What is K? K is specific constant, specific rate, or we say it is rate constant. Okay. Now we are decreasing the volume of that reaction mixture to half. What is the purpose? Because we want to increase the pressure. In order to increase the pressure by 2 times, what we are doing? We are decreasing the volume to half. So now instead of this V, what we are substituting, you see? V by 2, because volume is decreased to half. Let us substitute the new volume in this expression. So we get what? Rate is equal to K into number of moles of A divided by V by 2 whole power 2, number of moles of B divided by V by 2. If you are writing in proper way, rearrangement means the rearrangement of this, rate is equal to V by 2 square is there, you see. That's why we get the 4 in the numerator into 2. From the second term we can obtain it into K into Na by V power 2 into Nb by V. If you observe this new rate equation, in this, what is the value of K into Na divided by V power 2 into Nb divided by V? This is nothing but the initial rate. This is nothing but the initial rate. Means when you are decreasing the volume to half, rate is increased by how many times? 4 into 2 times, means 8 times the rate is increasing. So we can say if the pressure increases in the gaseous reaction, what happens? The rate of reaction increases. If the pressure increases in gaseous reaction, what happens? The rate of reaction increases. Why it increases? When you increase the pressure, volume decreases. Another point also we have to discuss here. What is that? The relation between the volume and concentration of gas. If the volume is more, for a particular mass of the gas, if the volume is more, concentration is less. Is it? At constant mass, if the volume is more, is it? Concentration will be less. Means the concentration and volume are related. How? Inversely proportional. So when you are decreasing the volume means what? You are increasing the concentration. When you are increasing the concentration, what happens? In the previous topic we were discussing that at higher concentration, the number of reactant molecules existing per unit volume will be more. The number of collisions will be more. So that rate of reaction increases. Okay, that is means the pressure increase in the gaseous reaction. What happens? The rate of reaction also increases. That we can conclude. Okay, next. Let me discuss about the effect of temperature. All of you know that when the temperature increases, the rate of reaction increase. The reaction which takes place in liquid phase or gaseous phase. When we increase the temperature, the speed of molecules increases, means the kinetic energy of molecules increases. When the speed of molecules increases, the number of collisions taking place between the molecules now increase at higher temperature. That's why rate of reaction increase. In most of the reaction, this was observation. What is that? That is, when a temperature of a reaction is increased by 10 degrees centigrade, when the temperature of reaction increased by 10 degree centigrade, what happened? The rate constant of reaction becomes double. This we see in many reactions. When you increase the temperature by 10 degrees centigrade, in any reaction, the rate constant becomes double. This can be observed predominantly in the vicinity of 15 degrees centigrade to 25 degrees centigrade. For example, a chemical reaction is there. For that chemical reaction, we are determining the rate constant at 15 degrees centigrade. It is K1. What is the rate constant of the reaction at 15 degrees centigrade? K1. For the same reaction, now we are determining the rate constant by increasing the temperature to 25 degrees centigrade. At 25 degrees centigrade, the rate constant of that reaction is now K2, let's say. So at 15 degrees centigrade, the rate constant is K1. At 25 degrees centigrade, the rate constant is K2. If we calculate the ratio between K2 and K1, that is K2 by K1, it will be approximately equal to 2 in most of the chemical reactions. So the ratio between the two rate constants, which are measured with a difference of 10 degrees centigrade, is called temperature coefficient. That is represented by mu. Mu is equal to, you can write like this, mu is equal to Kt plus 10 upon Kt. You are measuring the ratio between two rate constants of the same reaction. How these rate constants are measured? With a difference of 10 degree centigrade. Higher temperature rate constant divided by lower temperature rate constant. That gives approximately 2. That is the meaning of temperature coefficient. The effect of temperature on rate constant of reaction is explained by Arrhenius equation. The Arrhenius equation is d log k by dt is equal to delta H by RT square. It is generalized by Arrhenius as d log k divided by dt is equal to EA by RT square. What is delta H? Enthalpy change. Now it is replaced by EA. EA means activation energy. The enthalpy change is replaced by activation energy in the generalized equation. Okay. Next. In this, R is a universal gas constant, T is absolute temperature, K is a rate constant, d by dt is a differential operator. Integrating this equation, on integrating this equation, we get what? Integrating this equation, see, we are integrating this, we get the finally what? K is equal to A into e power minus A by RT. K is equal to A into e power minus A by RT. This is also called as what? Arrhenius equation. So different forms of Arrhenius equation we can observe here. Different forms of Arrhenius equation. Arrhenius equation explains the relation between the rate constant of reaction and temperature of reaction. There are forms or different forms of Arrhenius equation. Next. So Arrhenius equation is K is equal to A into e power minus A by RT. What is K? K is the rate constant. say it is K is the rate constant. Okay. Next, A is the frequency factor, or we say it is a exponential factor. Frequency factor or exponential factor, A. E is the mathematical quantity. Okay, in natural logarithm we use this E value or E term. T is absolute temperature, or is a universal gas constant, capital EA. Activation, actually it should be E small a. E subscript small a. Means these are the different terms which are mentioned in the Arrhenius equation. Next, when we are discussing about the temperature quotients, what we said, when the temperature of reaction increases by 10 degrees centigrade, the rate of reaction increases by, rate constant of reaction increases by 2 times. Why it happens? That we can explain with the help of this graph. This graph is drawn between the fraction of molecules versus kinetic energy. This we say the Maxwell distribution of molecular speeds, also we can say, because the kinetic energy is directly proportional to speed of molecules. In this graph, we observe the curves at 2 different temperatures, that is T1 and T2 temperature. At a given temperature, how the molecular speeds are distributed at low temperature or high temperature, whatever it may be, very few number of molecules will possess either low energy or high energy. Maximum number of molecules will lie in the medium range. So now you observe the T1 temperature. What about the molecular speeds that we can see? At T1 temperature. At T1 temperature, that is we are saying the lower temperature, this is a curve represented with blue line. When the temperature is increased by 10 degrees centigrade, means it's a higher temperature T2. The red curve explains the distribution of molecular speeds. At T1 temperature, you can observe the molecule which are possessing the high energy. The molecule which are possessing the high energy, they are called as activated molecules. Means this is a region where the activated molecules exist. So this area will be directly proportional to the number of activated molecules. If you calculate the area lying under this part, that explains what? The number of molecules possessing the activation energy. Now if you increase the temperature to T2, under those conditions, what happened? The speed of molecules, will increase. The speed of molecules increases, means the molecule which are possessing lower energy decreases, whereas the number of molecules possessing higher energy increases. In this process, we see the number of molecules possessing higher energy now becomes double. This area represents what? The number of molecules possessing activation energy. Now, if you calculate the ratio between the number of molecules at lower temperature and number of molecules at higher temperature means when you, after increasing the temperature by 10 degrees centigrade, it will be approximately double. That's why the rate constant calculated with the difference of 10 degrees centigrade will be approximately equal to 2. We call it as what we call temperature quotient of reaction. Temperature quotient of reaction. Like this we can explain the meaning of temperature quotient with the help of this graph. And also have to discuss about the concept of activation energy, because in Arrhenius equation, activation energy is represented. What is meaning of activation energy? If a chemical reaction is considered at room temperature, normally at room temperature, how the molecule speeds will be distributed? the molecular speeds will be distributed from low speeds to high speed. Means all the molecules will not possess the same kinetic energy. They will possess different energies. Among these reactant molecules, only few molecules will possess a minimum energy. They will possess what? A minimum energy or greater than that minimum energy, so that they will form the products after collision among them. Means, in order to convert the reactant into products, the reactant molecules must possess a minimum energy. The minimum energy possessed by the reactant molecules to form the products after collision is called as threshold energy. So in this graph, it is represented a graph between what? Energy and reaction progress. Actually, we say reaction coordinates. Reaction coordinate, energy versus reaction coordinates, reactants and products. In order to convert the reactants into products, these reactant molecule has to cross over the energy barrier. They have to cross over the energy barrier. But all the reactant molecule will not possess the same energy. The molecule which are having the enough energy, they only react with each other to form the products. Means, if the energy of molecules is equal to threshold energy, this line indicates threshold energy, they only form the products in the reaction. We represent this threshold energy with what? ET. Energy of normal molecules, we say it is En. If you calculate the difference between ET and En, this is called activation energy. So activation energy is the difference between the threshold energy and energy of normal molecules. That is the meaning of activation energy. So this graph is drawn between energy versus reaction progress or reaction coordinates. So threshold energy means the energy possessed, minimum energy possessed by reactant molecules to form the products in the reaction. That is meaning of threshold energy. Next, let us see about the activation energies of exothermic and endothermic reactions. What is the meaning of endothermic reaction? The reaction which takes place by absorption of heat. That is called as endothermic reaction. The reaction which takes place by absorption of heat. In endothermic reaction, the energy, if you see the energy of reactants and products, the energy of reactants will be less compared to the energy of products. Means lower energetic reactants are converting to high energetic products. In order to convert the low energetic products into low energetic reactants into high energetic products, how it is possible? Just by absorption of heat. Is it so? The absorption of heat, it is enthalpy of reaction, we can see here, enthalpy of reaction. So this is the energy difference between the energy of reactants and energy of products. So we can see the activation energy of forward reaction. This is the activation energy of forward reaction. Similarly, this is what? Threshold energy. What is the activation energy of backward reaction? This is the activation energy of backward reaction. So activation energy of forward reaction will be equal to the sum of activation energy of backward reaction and enthalpy change. This we can see in the case of endothermic reaction. So activation energy of forward reaction will be equal to activation energy of backward reaction plus enthalpy change. That we can observe in the case of endothermic reaction. Now we see about the exothermic reaction. What is the meaning of exothermic reaction? The reaction which takes place by evolution of heat or release of heat. In this, the energy of reactant molecules will be greater, where the energy of products will be less. Means high energetic system is converting into low energy. When the high energetic system is converting into low energy, what happens? energy is released. This is the amount of energy releases in this equation. We say it is enthalpy change of that reaction. What is the threshold energy of this reaction? This is the threshold energy. This is a threshold energy. Okay. Now you can see here the threshold energy given by this is it. What is the relation between the activation energy of forward and activation energy of backward? The activation energy of backward reaction is more than the activation energy of forward reaction. This is the activation energy of forward reaction. Whereas the activation energy of backward reaction is this one. Which is greater? The activation energy of backward reaction is greater than the activation energy of forward reaction. So what is the relation between these activation energies of both forward and backward reactions? Now we say the activation energy of backward reaction is equal to sum of activation energy of forward reaction plus what? This energy released means enthalpy change. Okay, it is activation energy of forward reaction, this part plus energy release in the reaction. That will becomes equal to activation energy of backward reaction. Like that we can see. So here one important point we can observe. What is that? You remember the threshold energy of for both activation and the threshold energy for both forward and backward reaction will be same. There will be no change. Is it? With respect to that only we can measure the activation energy. We can express the activation energy. Next, this is the concept of activation energies in case of endothermic and exothermic reactions. Again, we are discussing about Arrhenius equation because we want to calculate EA. How to calculate EA? EA means activation energy. Here we are writing about the logarithmic form of Arrhenius equation. Log K is equal to minus A by 2.303 RT plus log A. Log K is equal to minus 2.303. Log K is equal to minus A by 2.303. Yeah. Plus log A. This is a logarithmic form of Arrhenius equation. Now we are carrying a reaction. We are performing a reaction. How? At two different temperatures. The same reaction is taking place at two different temperatures separately. Let's say only temperature is different, remaining are the identical conditions. Initially, the reaction is taking place at T1 temperature. Then what is the rate constant observed? K1. We know that the rate constant depends only on temperature. It is not altered by the concentrations of reactants. So K1 is the rate constant at T1 temperature. So this is Arrhenius equation. Equation number 1, log K1 is equal to minus A by 2.303 RT1 plus log K. Similarly, the reaction which takes place at T2 temperature, the same reaction, but it is taking place at T2 temperature. What is the rate constant? K2. So according to Arrhenius equation, log K2 is equal to minus A by 2.303 RT2 plus log A. This is equation number 2. If you subtract equation number 1 from 2, we get what? Log K2 minus log K1. What is log K2 minus K1? Log K1. It is log K2 by K1. We get this equation. Log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. Okay, this is about the Arrhenius equation represented at two different temperatures. With the help of this equation, we can calculate the activation energy of reaction. This is a very important equation. K1 and K2 are the rate constant at T1 and T2 temperatures respectively. R is the gas constant. So if you are calculating this K2 and K1, T2 and T1, and you can substitute R value in joules or calories or X mole inverse Kelvin inverse, so that you can calculate what? EA. So with the help of this equation, we can calculate activation energy of reaction. It's a graphical representation. How can we determine the activation energy with the help of the graph? One is with help of Arrhenius equation we calculate EA. Second, with help of the graph also we calculate EA. For both of these, the same data is required. What is the data? Temperature and K. So this graph is drawn between log A versus 1 by T. So if you observe this equation, log A is equal to minus EA by 2 point minus EA by RT plus log A. It is present in the form of y is equal to mx plus c. But what is the tangent? B represent tangent here. It is minus EA by R, means it is a negative. So log A versus 1 by T is a straight line with negative slope. The slope of the straight line is equal to minus EA by R. This is just by drawing the graph between log A versus 1 by T, we get a straight line. Slope is equal to minus EA by R. Let's solve one problem according to Arrhenius equation to calculate activation energy. This is a problem given. The rate constant of reaction is doubled, raising the temperature from 300 Kelvin to 310 Kelvin. Calculate the activation energy of reaction. So, rate constants are given and temperatures are given. You have to calculate the activation energy. Now, we are writing the activation Arrhenius equation, which represents two different temperatures and two rate constants. Now, K2 is equal to 2K1, because when you are increasing the temperature by 10 degrees centigrade, K2 becomes double. That's why instead of K2 we are writing 2K1. Here we are substituting, you can see, divided by K1. That is equal to EA by 2.303. R value is 8.314. Actually it is 8.314. 1 by 300 minus 1 by 310. So everything is known. K1 and K1 will get cancelled here. So everything is known except what? EA. So EA is obtained as 53,598.6 joules or 53.598 kilojoules. Like this, by substituting the K1 and K2 values at two different temperatures, you can calculate activation energy. So activation energy can be calculated with the help of Arrhenius equation. Next, another factor which influences the rate of reaction is medium of reaction. The reactions occurring between reactant ionic reactants takes place at different rates in solvents of different dielectric constant. And so if we change the solvent, what happens? The rate of reaction also changes. Ionic reactions will be favored by polar solvents like water. The solvents which are having the high dielectric constant will facilitate the ionization process. That's why rate of reaction will be more. But whereas the molecules are neutral, if the neutral molecules are participating in the reaction, the influence of solvent is very little. So ion reactions are favored by polar solvents which are having dielectric constant, more dielectric constant. Whereas the reactions occurring between neutral molecules will not have the effect of solvent. It will be very little viscous. Very familiar example we can quote here. What is that? The rate of SN1 reaction is more in presence of polar solvents. What happened in SN1 mechanism? In first step will be the ionization process. If you use the polar solvent like alcohol or water, what happened? The rate of reaction will increase. Whereas the effect of solvent is very less in case of SN2 reaction. So medium of reaction is one of the factors that influence the rate of reaction. Next, effect of radiation. Radiation energy is nothing but electromagnetic radiation like visible, UV, IR, microwave, etc. In photochemical reaction, you know about the photochemical reaction, the reaction which takes place in presence of light. In photochemical reaction, this electromagnetic radiation plays important role. You can observe the example H2 and Cl2. The reaction between H2 and Cl2 takes place in presence of sunlight or visible light. As the intensity of light increases, what is the meaning of intensity? The number of photons falling per unit area. According to laws of photochemistry, each molecule will absorb only one photon. Correct or not? Each molecule will absorb only one photon. According to that, If you increase the intensity of light, what happens? The number of reactant molecules participating in the reaction also increases, so rate of reaction increase. So the rate of reaction will be directly proportional to intensity of radiation. In photochemical reaction, radiation also plays important role, and also it will produce the heat in the reaction. Another factor which influences the rate of reaction is effect of catalyst. What is the meaning of catalyst? The substance which can increase the rate of reaction when it is added to reaction. The catalyst will participate in the reaction, it increases the rate of reaction, finally it will release in the same quantity as it is at the end of the reaction. In many organic reactions, we can observe this feature. With the help of this graph, we can explain the effect of catalyst on rate of reaction. As we discussed, the activation energy is less, rate of reaction will be more. Means the rate of reaction and activation energy are related inversely proportional. So when the catalyst is not present in the reaction, you can see this red line. When the catalyst is not used in the reaction, this is the energy barrier, high energy barrier. When we use the catalyst in the reaction, then what happens? The reaction will change its mechanism. How? It changes mechanism with lower activation energy instead of higher activation energy. Means what is happening here? That is, threshold energy is decreasing, means activation energy of reaction decreasing. Due to change in mechanism of reaction, the activation energy decreases. When the activation energy decreases, what happens? The speed of reaction will increase. So, in presence of catalyst, the threshold energy of both forward and backward reaction will decrease to same extent. That's why both the forward and backward reactions will speed up to same extent. Okay, so catalyst will increase the speed of reaction. It is due to decrease in activation energy. This is about the effect of catalyst on rate of reaction. Thank you.